Welcome to this presentation on HDFS directory structure and configuration files. Today, we'll delve into the key storage components in directory architecture that support the Hadoop Distributed File System, or HDFS. We'll also explore the configuration files that control how HDFS operates in both development and production environments. HDFS, or Hadoop Distributed File System, is designed to store very large files reliably and to stream those data sets at high bandwidth to user applications. It achieves this by storing data in large blocks, typically 128 or 256 MB in size. HDFS has two core layers: the namespace layer, which manages metadata through the name node, and the block storage layer, which stores the actual data and is managed by the data nodes. Additionally, we rely on several local disk directories on each node to store critical metadata and data blocks. The name node plays a crucial role by storing the file system's metadata. This includes the directory structure, file names, and block-to-file mappings. This metadata is saved in directories defined by the property dfs.namenode.name.dir. By default, this path is located at $Hadoop TMP dir/dfs/name. In a production setting, however, this path is usually set to multiple directories to ensure high availability and durability of the metadata. In production, the NameNode directories are often configured to point to multiple disk volumes such as /nndateon and /nndatedwo, as shown in this XML snippet. This setup allows the use of RAID on multiple disks, which provides redundancy. This means if one disk fails, the metadata is still available from the other. Within each NameNode directory, we find several key files. fsimage xxx is a point-in-time snapshot of the file system metadata. Edits xxx logs all recent changes to the file system, and cntz records the transaction ID of the last edit applied. These files are essential for maintaining and restoring the state of the HDFS namespace. While the name node handles metadata, the data nodes handle actual data storage. They store HDFS data blocks in directories specified by the property dfs.datanode.data.dir. Similar to the NameNode setup, the default path is under $Hadoop TMP dir/dfs/data, but production environments typically use dedicated disks. In production, DataNode directories are configured to utilize multiple paths such as /dndateon, /dndatedwo, and /dndata3. This approach helps balance the load across multiple disks, improving performance and reliability by avoiding single points of failure. The internal structure of each DataNode directory contains subdirectories under a path named after the block pool ID. Under current /, you'll find directories like RBW for blocks being written and finalized for blocks that are fully written and ready for replication. Each block has a data file and a corresponding metadata file, such as blkxxx and blkxxx-meta. The secondary name node isn't a backup, as commonly misunderstood. Its main role is to periodically merge the fsimage and edits logs to create a new checkpoint. This is configured through the dfs.namenode checkpoint dir property, where checkpoint data is stored, typically in a directory like /sn/checkpoints. In addition to the checkpoint directory, the secondary name node also stores intermediate edit logs. These are configured using the dfs.namenode checkpoint edits dir property. Keeping checkpoints and edit logs in separate directories helps maintain organization and supports failure recovery. All major configuration files for HDFS are found under $Hadoop home/etc/Hadoop/. The most critical among them are hdfs-site.xml and core-site.xml, which define operational parameters. Other files include workers listing DataNode hosts and Hadoop n/sh, which sets environment variables. In hdfs-site.xml, we define key properties that govern HDFS behavior. For example, DFS replication sets the number of replicas for each block, usually 3 for fault tolerance. DFS block size defines the block size, with a typical value of 134,217,728 bytes, or 128 MB. Other important settings in hdfs-site.xml include dfs.namenode HTTP address, which specifies the HTTP port on which the NameNode web UI runs. This is vital for monitoring and administrative purposes. Moving on to core-site.xml, this file contains the foundational settings for Hadoop. One of the most important is default fs, which defines the default file system URI commonly set to the NameNode host and port. This configuration determines how clients connect to the HDFS cluster. Another core setting is Hadoop TMP dir, which specifies the temporary working directory used by Hadoop for storing intermediate files. This should always point to a reliable and persistent storage path like /op/hadoop/tmp rather than the system/tmp directory, which may be cleared upon reboot. Here are some best practices for managing HDFS directories. Always use multiple disks for both NameNode and DataNode directories to enhance performance and fault tolerance. Never use volatile directories like /tmp for storing HDFS data. Instead, configure Hadoop TMP to a dedicated and persistent location. When issues arise, here are a few troubleshooting tips. If you encounter metadata corruption, use the command hdfs-namenode recover. For missing data blocks, examine the DataNode logs. And if you suspect configuration problems, run hdfs getconf key to verify effective settings. To wrap up, the NameNode handles all metadata using files like fsimage and edits. DataNode store the actual block data across multiple directories. Critical configuration files include hdfs-site.xml and core-site.xml. Always remember to back up your metadata and monitor your disk health regularly to ensure a robust HDFS deployment.